Welcome to this morning's presentation. We're going to cover proxy patterns and how to upgrade your smart contracts on Ethereum-based chains. My name is Chris Cordle. I'm an integration engineer at Offchain Labs. We were the initial creators of Arbitrum, and we continue to support Arbitrum DAO and the foundation in all their efforts to build and grow Arbitrum in the Arbitrum ecosystem. To start off, I've got to cover the most exciting thing that's perhaps happening on chain today is that the financial world, it's the blockchain is eating the financial world. Smart contracts are currently revolutionizing traditional finance. A lot of existing players like PayPal, Walmart, Robinhood, Revolut, Stripe, etc. They're looking at issuing stablecoins or integrating stablecoin payments into their business, and it's just an exciting time to be in the space. So why are these TradFi projects so excited about programmable money, which is what Ethereum enables and unlocks through standards, token standards like the ERC20 token standard, which can tokenize any fungible asset. So that includes dollars, euros, rupees, stocks, whatever your asset might be that you're interested in tokenizing. There's a way to get it done with the ERC20 standard. Um, Meanwhile, smart contracts unlock this programmable logic that allows you to escrow funds, facilitate 24/7 trades, process loans, and a whole lot more. And basically, this unlocks value and allows it to flow freely across borders, across 24/7. The blockchain never shuts down, so everything just keeps moving. So smart contracts, they execute deterministically. When we say that, that means that there's a guarantee that if the logical rules of the contract and the blockchain it's hosted on are followed, then it's guaranteed to execute. It's kind of like a vending machine that never jams. So you put your dollar in and you get your Coke out. It never runs out of supply. It never, it never jams. It never fails. It just spits out the Coke and you're good to go. So smart contracts on Ethereum, they're immutable, which is great. A contract by definition has fixed terms, right? So, two parties agree ahead of time what those terms might be, and smart contracts try to emulate that in the on-chain world. However, what if you need to make a change? What if you need to alter the deal? Well, there is an art to it. Immutable contracts are great, but they don't factor for needs of some products. What if you need to add a new feature, accommodate a new standard, fix a bug? In trad software, you would just push a change to the server and then redeploy. But how can we create mutable contracts from immutable deployments? Well, while we can't change the code, we can change the state of those contracts that we have deployed. So we'll use a tool called delegate call, which is a feature of Solidity that allows contract A to call into contract B as if it's being invoked by contract A itself. This uses, again, the state space of contract A when it's calling into contract B, delegate calling into contract B. All the state updates are occurring as if it exists in contract A itself. It's kind of like giving a bookkeeper access to your checking account, say, go ahead, handle my bills for me, and I'm just going to delegate this responsibility to you, bookkeeper. So there's tons of use cases for delegate call in the Ethereum ecosystem, but especially unlocks the proxy pattern, which is what we're talking about today. So in a nutshell, here's kind of a super basic diagram for how proxy patterns work. You've got when a user calls into the proxy contract, it invokes what's called a fallback method on that proxy contract, which then delegate calls into the implementation contract. And you notice we had V1 originally, and then at some point, the admin upgraded the proxy to point to V2 so that anytime the user while the user originally was calling into V1 essentially by proxy, now because it's been upgraded by the admin, it's been delegate called to the new V2 implementation contract. So this is just in a really basic nutshell how the proxy pattern works. It's quite um, simplified from the existing implementations you'll see, but if you understand this diagram, then you really understand proxies ultimately. Um, and you understand how the upgrade process works and how you've got your implementation contracts and your proxy logic, which could be in a single contract or split into two contracts in some implementations. All right, let's go over some key definitions. If you don't understand it totally yet, let's go over some key definitions and hopefully you'll get it. Proxy contracts, as we covered, it's the fixed entry point for users to interact with. It is a source of truth for your application, and it is the public address that users will call into. A lot of times this is abstracted away on the front end, and the front end itself is calling into a proxy contract. And it's not users themselves and specifically typing in an address, but it's a website that's got some JavaScript logic that's calling into that proxy address. So, but that is the public address that users and apps use to interact with your application. The proxy contract is fixed, doesn't change. It contains ownership info. It may have addresses to one or more implementation contracts and may include the logic for upgrading, although that could be placed somewhere else as well. But for the basic example that we'll cover later, it will contain the upgrade logic and the admin logic. The implementation contract contains all the business logic of your app. So if you've got an exchange or some kind of token that you're deploying, well, that would be your actual ERC20 contract in the example of a token, or it could be something more complex like a DAO. Either way, your business logic is represented in implementation contracts. No implementation details go into the proxy itself. This is what we're hoping to be able to upgrade in the future if we need to alter the deal. So, um, yeah. Other definitions are storage management. Proxies often use specific storage slots defined by the EIP 1967, a great year for Mustangs, especially to store metadata like the implementation address, avoiding collisions with the implementation's variables. So, the storage management is sort of like your strategy for storing data in specific slots, which I'll cover a little bit more in an upcoming slide, how storage works in Solidity and Ethereum. But it's important to note that there's different approaches to this. EIP 1967 is one such approach and is the default um, storage strategy that proxy contracts use in Ethereum. Upgrade mechanism is the logic that changes the implementation contract to a new contract address. It's usually restricted to the admin or owner of the proxy contract itself. All right, let's go over a couple more Solidity concepts. Number one, a couple of basics. Catchup 256, if you're not familiar, it's a hashing function commonly used to get a 32-byte value from any, it's a pseudo-random output that's from any arbitrary linked inputs. You put in any number of bytes into the catchup 256 function, and it will output you always a 32-byte value. And this is a heavily used hashing function in Ethereum, and it's used by Solidity itself under the hood in many cases to organize code and handle routing logic and things like this. And there's also another function that we covered earlier called the delegate call. So these are functions of Solidity that you can use in your code and that are actually used in proxy implementations to implement the logic for proxies. function selectors. If you're not familiar with function selectors, they are sort of abstracted away from you. If you're a beginner in Solidity, you may not realize, but every public or external function you define gets assigned a 4-byte selector by Solidity. And in order to get, in order to, the definition of that, of each, of the selector for each function is determined by its function name. The catch hash of its function name and the parameters and the type parameters of the function. Um, and that it takes that as a string, it hashes that string, and then it slices off the first 4 bytes from that 32-byte output. So Solidity at this is not something you need to be totally up and up on if you're a beginner, but ultimately, if you're familiar with router patterns or handlers from web servers, Solidity sort of does something similar behind it kind of transforms your top level contract into a router, and then it routes to the functions based on a 4-byte value that's passed in as raw binary transaction data whenever you're invoking a smart contract. So essentially, you look at the byte data of a transaction, and always the first 4 bytes are interpreted by Solidity contracts to be the function selector, and it's used to route the call to the proper function selector. So this occurs, this is abstracted from you as a developer, as a beginner developer in Solidity, but it's an important thing to note. So Solidity also has a concept of a fallback function. This is an optional function you can define on your contract, which will be invoked if an external caller includes a 4-byte header that is not defined as the public ABI for that contract. So in other words, if somebody tries to call into a contract with some and tries to invoke essentially a function that's not defined on that contract, you can optionally define a fallback function that will handle the transaction data that's being passed in. So easy way to think about it is kind of like a default case in a switch statement in a normal programming language. It's sort of like that. It's relevant to proxies because it allows the proxy contract to forward the transaction data and delegate call that data to the implementation contract. So essentially, when you're calling into a proxy contract as a user, and let's say you're trying to like mint a token or something like this, you're trying to get to the mint function, which is defined on the implementation contract. Well, you're going to send that transaction to the proxy, and the proxy is going to forward that transaction data to the implementation contract because it's not going to have a mint function on the proxy itself. It's on the implementation contract. So since it doesn't see it as part of the proxy's publicly defined methods, it delegate calls to the implementation contract. And that's under the hood. That's essentially how proxies work. Yeah. And that's essentially how they work. And 1 second. So, okay. That covers fallbacks. Now let's cover storage slots. So each contract in Ethereum has 2 to the 256 possible locations it can store 32-byte variables. So this is the way storage is arranged in Ethereum and in Solidity. You've got a huge address space of possible slots that you can store, possible keys that you can store 32-byte values in. So you got that many 32-byte buckets that you could theoretically store contract data into. By default, Solidity stores variables in slot 0, then slot 1, and then so forth based on their order of definition. There's some additional complexity, by the way, with mappings, nested structs, and arrays. I won't get into that for this presentation. I highly recommend you watch or look up on Solidity docs for how storage layout works. But ultimately, if you think of it as for primitives like uints and addresses and things like this that are defined at the top level on Solidity, it's just going slot 0, slot 1, slot 2, based on what and it's trying to slot them into 32 byte sections. Um, and it handles all this automatically for you. It's not something you have to think about. It's a feature of the Solidity language. But ultimately, this is what Solidity is doing under the hood when it organizes your data for the EVM, the Ethereum virtual machine, to interpret and to store and retrieve. Um, it's important to note here because the order of defined variables affects which slot they're stored in under the hood. And this is important when upgrading smart contracts, right? Because your proxy contract is your source of truth. It is the state space that is being used by your implementation contracts when it's delegate called into. And when you upgrade your contracts to a new version, you have to be careful to maintain the same order of definition of state variables, because otherwise the slot may change and you could inadvertently overwrite a value that you didn't mean to. So generally speaking, when you do an upgrade in Solidity, you append only new state variables. You do not delete, modify, move pre-existing state variables. Um, it's just not worth it, and it has a lot of pitfalls there. So generally speaking, only append state variables and append new methods, generally at the top level contract only. Um, if you try to, if you try to modify the order of inherited contracts as well, that can affect the slot order as well. So, it's just generally append only when you're upgrading. Keep that in mind. 1967 is an EIP, which is an Ethereum improvement proposal that was proposed a couple of years ago. It defined a standard for defining the slots that admin addresses and implementation addresses are stored in for proxy contracts. It also standardized a few events like admin changed, and it helps, tooling like Etherscan and explorers to grok and understand proxy contract implementations. It also kind of helps prevent storage slot conflicts, which is nice. Um, as an example of where the proxy admin address is defined, where the slot of the proxy admin address is stored, it uses the catch-check hash of the string EIP 1967.proxy.admin, subtracts by 1, gets the hash, interprets that as a bytes 32, and that is the slot that your admin address is stored in if your proxy complies with the 1967 standard. So proxies are risky, a little bit risky. Upgrading contracts, like we said before, um, you know, you almost want a default to immutability, because upgradability in smart contracts, especially when you're dealing with real money, has a lot of pitfalls because of how state and behavior are changed and upgraded and interpreted in Solidity and in Ethereum. So there's been lots of historical fails with proxies. One of the most notorious ones is the parody multi-sig hack from July 2017. They had a proxy-like architecture that had a minimal wallet contracts. These were like smart contract wallets that delegated calls to a shared wallet library for the logic. the library had an init wallet function. So each instance of the smart contract wallet would delegate into this wallet library, but it had an init wallet function that didn't prevent reinitialization. So a wallet could be initialized with some variable or some value, and then um, it didn't prevent that from um, being reinitialized. So it allowed an attacker to exploit this by resetting the owners of several high value wallets, and it drained $31 million in ETH at the time. It's probably worth a hell of a lot more by now if you do the math on what the Ethereum price was in July 2017 and compare it to today. Um, that was an unfortunate um, hack that affected the early Ethereum ecosystem. Another exploit of the same library occurred in November 2017, where a user set themselves as owner via Net Wallet and then invoked a kill function to self-destruct the library itself. So now all these implementation contracts that were relying on this library um, were don't no longer the library contract it was delegating to no longer exists. Essentially in this case. Now, in at the time, self-destruct would delete a contract's code, and this has been recently nerfed in Ethereum such that self-destruct isn't as powerful as it used to be. It can only be invoked in some cases, and it can't be only it basically just returns money from a contract these days unless it's invoked in a constructor. It doesn't delete the contract code anymore. So this exploit is technically not possible anymore because of changes to the self-destruct opcode itself in the EVM, but it's still something to note as a historical example and something to watch out for. Generally, just avoid self-destruct altogether. Um, you know, in your implementation contracts. It's not really useful these days anyways, and it's not necessary. ADS also had a governance exploit. There was a storage collision, as we mentioned, the 1967 standard that helps avoid that. Allowed an attacker to overwrite some critical variables and basically executed a malicious governance proposal and transferred 18 million audio tokens, which was worth about 6 million at the time, to their wallet. So this was just storage collisions between the proxy and the implementation allowed the attacker to overwrite critical variables. So, existing standards, as I mentioned, there were standards like the 1967 standard and other best practices that developed later on in Ethereum's life cycle. And, we've come to a point now where where um where sorry, that was a duplicate side there. Where there's existing battle tested open source implementations of proxies that you generally want to reach for. Like you may want to, try implementing your own proxy for fun and for education. But um your default should be to reach for an audited, battle tested, open source implementation of a proxy pattern that has been audited by a reputable auditing firm, has been maybe in use by major protocols for many years. Something like the transparent upgradable proxy by Open Zeppelin. This contract is probably your default, your de facto standard that you should probably um, reach for when you want to implement an upgradable proxy pattern. Um, it separates admin functions from user interactions. It handles a lot of this logic for you, and because it's been battle tested, you don't have to worry so much about the pitfalls and the fails that I just showed to you. So these are open source. They're there for you to reach, and I'll demo specifically the transparent one after a couple more slides. So covering there's a slightly different pattern called universal upgradable proxy. or UUPS for short. It's a lightweight proxy. It has reduced gas costs. It's more flexible for decentralized upgrades, and especially when those contracts are controlled by like a DAO or governance system. So it's just more flexible for these types of upgrades. But when you're just an individual or a startup, um, you may not need this. You may be fine with the transparent proxy, and the transparent proxy should be default. It's simpler because in a UUPS, the upgrade logic is um, is defined in the implementation contract itself. So it's a little hairy in those details, and getting those right is hard. So again, by default, you should probably just stick with transparent proxy. But if we do use it on our Arbitrum for our DAO and for our contracts, so it is used extensively, but it's a more advanced pattern you should reach for later when you know you need it. There's a couple of other patterns. Again, these fall into that. Only reach for them if and when you know you need them. But to go over a couple quick ones, beacon proxy is a proxy that points a shared beacon contract, which holds a current implementation address and allows multiple proxies to upgrade simultaneously. This is mainly useful for something like a smart contract wallet. Like, you could upgrade the implementation contract simultaneously for thousands of wallets by just updating the beacon contract um, through this pattern. The diamond proxy is another one. It kind of splits it allows you to define multiple implementation contracts and just sort of like define these little facets and these pieces that your contract logic breaks down into. So this allows you to just break up implementation contract into as many contracts as you want. You can kind of isolate concerns and upgrade concerns one at a time. It's mainly used in gaming and things like this, but it's an interesting pattern. Not I won't be covering it in more detail today, but it's something to consider down the road once you get more advanced in proxy deployments. So let's go in to how to implement the transparent proxy. Okay, I'm going to show you how to add upgradability to your smart contract project in the easiest possible way. This abstracts a lot of complexity, allows you to get going really quickly, and it uses a tool called Foundry, which is a fantastic CLI tool that if you're a Solidity dev, you should pick up and you should learn. It's a very powerful tool. If you don't have it already, make sure you have it on your system. Called Foundry up dash dash version. Let me switch over to my terminal so you can see what I'm doing. Called Foundry up dash dash version. If you don't have it, then you need to install it. Go to getfoundry.sh in your web browser to look at the instructions for how to install Foundry. And then once you've got that installed, you can come back to this part and we'll explain the rest. But for now, we're going to move on. This demo also uses a library called OpenZeppelin Foundry Upgrades. So OpenZeppelin is the creator of many of the most popular proxy implementation contracts that exist in the Ethereum ecosystem. They're a great auditor, fantastic tool builders for the whole Ethereum ecosystem. And these tools are open source and free to use. And they also created a utility library for Foundry itself that helps Foundry developers get going super quickly with proxy upgrades. And it's one of the easiest ways that I've seen to do proxy upgrades. Um, so without further ado, let's go ahead and initialize a new project. So we're going to use the CLI tool that comes with Foundry called Forge. And then we're going to invoke the init command on Forge, and we're going to go ahead and initialize a new Foundry project called My Proxy Project. And we're going to CD into that once it's set up. CD into My Proxy Project. Then we're going to install a couple of dependencies that we need in order to do this in the easiest way. And that is from OpenZeppelin's Open Zeppelin Foundry upgrades library, and their Open Zeppelin's contracts upgradable. This is a mouthful, but if you just go on to Open Zeppelin's website, you can look at these instructions. If the video is too fast for you, or you can pause and return. And we'll also include in the show notes links to a GitHub repo with these instructions so you can follow along. Don't worry if you can't keep up on your keyboard. I'm going to fast forward through a lot of these commands so that we can just move on with the video. But while that's installing, I'm going to pause. And we're back. That was a quick installation. Fantastic. Let's move on. We're going to create a file called remappings.txt. And in this file, we're going to add a couple of Open Zeppelin settings that it needs. So we're gonna add those remappings that it wants for everything to work good with our project. We also need to edit our foundry.toml file. And we're going to add a couple of settings here that Open Zeppelin likes to have so that it can check and validate your upgrades before you actually upgrade them. Again, proxy contracts have lots of pitfalls. If you try to enroll your own proxy and try to do a number of things when you're upgrading the implementation contract for your proxy, this tool will check a number of things and try to check a number of pitfalls that you might fall into, and warn you about them or stop the deployment or the upgrade process before you make a big mistake in production. But useful for while we're testing locally, it's still useful for us to have all those checks here. So we're going to add them here, and then we're going to exit back out into the main directory. Now we're going to invoke forge build. Just make sure with this new TOML upgrade that everything works good. We set the TOML correctly. Forge build works. That means everything compiles. Now we're going to create a new terminal window, and over here we're going to invoke a command called Anvil. Anvil is Foundry's tool for creating a local blockchain that you can just use as a test environment. It goes ahead and sets up some accounts with some test ETH, 10,000 ETH each, and the private keys associated with each of those addresses. And it deploys this to the local address, local host at 8545 port number. So that's going in the background. That's again a Foundry tool called Anvil, and you want to run that in a separate window or a separate pane in your terminal. Then we're going to go ahead and look at the code itself. So let's go ahead and go into Vim. And I'm using Vim for this, but you can use whatever editor tool that you want. I'm using NeoVim in this specific case, but you're welcome to use VS Code, whatever you need. And we're going to go ahead and look at the default counter that's deployed along with Foundry's default project. So you've got basically a number value there. You've got a set number method. You've got an increment method. And this is just, your basic counter hello world demo that Foundry projects are initialized. So we're going to delete all that and we're going to create our own counter. And I've only changed a couple of things here. First, I've imported this initializable utility contract from Open Zeppelin, and I've made the counter to inherit from that initializable contract. So with that, it inherits some logic that allows us to set up what is the equivalent of a constructor for this counter. Now, the reason why we need to do this is because implementation contracts and proxy contracts have totally different addresses. And when the counter itself is deployed, constructor is run in that context, in the context of the deployment address. But since we're using the proxy pattern, we don't want that. We want the function to run in the context of the proxy contract itself. So OpenZeppelin creates this tool that allows you to easily define one-time use functions such as initializing your counter to an initial value that it starts at. So you can see here, we've just added the decorator of initializer where it adds in additional logic behind the scenes that makes sure that this function is only ever invoked one time, and that is going to be during the deployment of the proxy contract and the initial implementation contract itself, but never again. We're going to set the number to that initial value, and we're good. So this is the equivalent of a constructor or an implementation contract that intends to be run and executed only by a proxy contract, and that is the case with our demo here. So with that, we're going to go back out to our project. We've got our counter contract. We're going to go back out to scripts now. We're going to, what we're going to do here, we're going to delete the existing script here. Actually, we don't need to delete it. We're just going to create a new script, and we're going to call it deploy.s.sol. And from here, we're going to add in a Foundry script. And again, I'm going to add a lot of boilerplate and fast forward through a lot of details. But you'll want to either pause this or use the referred README in the notes in order to implement this yourself. But that's a lot of typing. But essentially, we're just importing the script tool from Forge, console Forge contract, so that we can log values out to the console when we run these scripts. We're importing the upgrades utility library contract from OpenZeppelin and the counter we just defined. And this upgrades contract is what we're going to actually use to deploy the proxy contract, the transparent proxy contract. And it's going to essentially, what we're doing here is we're setting that address as the proxy contract. We're going to go ahead and run upgrades.deploy transparent proxy with a reference to the counter contract that we just defined from our source directory. This is going to be the initial admin or initial owner of the transparent proxy, defaulting that to message.sender. And then we're going to invoke that initialize function that we defined in the previous step. And I'm going to go ahead and initialize it at 2. And that's going to let us, don't worry about these errors up here at the top. That's the import. This is correct. It's just my tool. My checker tool is off, but it should run correctly in a Foundry context. But we're going to go ahead and invoke that initialize function, set the counter to 2. Then we're going to output that to the console. Then we're going to increment it by 1 and output that to the console. Now, how do we do that? We quit out. And let's go ahead and forge clean and forge build to recompile everything in our project. Now we're going to run a script command that will run this is a forge CLI command that runs the script command. And then we're just invoking the deploy contract against the locally hosted Anvil chain with the private key that ends in FF80, which is what Anvil gave us when it deployed. And then we broadcast that transaction, and it goes ahead and runs. And it goes ahead and gives us some logs. And you see here, we've got the proxy address here that it outputted. We're going to go ahead and copy paste that to our clipboard, or we might have to come back to this later because we have a few other things to copy paste. But for now, notice that it's initialized the value remember from the script, it initialized the value at 2 and then it incremented by 1. So we got that 3 to come out perfectly fine. So that is from the console logs itself. Below that, you can see some more metadata about the transaction itself. And it includes like that's the implementation. That's the address of where the implementation contract was deployed right here. So first we deployed the implementation contract. Then we ran the initialization, or then we ran the then we deployed then the script deployed the proxy contract itself, and it deployed it at 512, and everything worked fine, and it output the values as we went. So that's good. Everything worked perfect. So now, what do we do to upgrade that contract? Now that we've got the proxy is sitting in front of the implementation contract, we now need to create some upgrade logic. So let's go ahead and go back into our project. We're going to go back here to source, and we're going to create a new version of counter called counter v2. Then we're going to go ahead and I'm going to copy and paste from some stuff I wrote earlier. And I've only changed one thing from our earlier implementation, and that is I've added this multiply function, which allows us to multiply the counter value by the counter number by some arbitrary value. That's great. Now we can save that and go into back up into. We're going to create a script now that runs the upgrade itself. And for this, we're going to create an upgrade.s.sol. And again, I'm going to paste in some boilerplate. Let's go down here. Let me copy over from my other window that you can't see. Now, here I've added this new upgrade script. I've imported an additional options contract that we need in order to set up Open Zeppelin. So in the logic itself, we need first I define the proxy address here. Notice I've said that you need to change this to your implementation. So that is because every time you deploy a new proxy, um, you need to get that value, which is the right here in the terminal on Anvil. It's over here, but you can also exit back out of Vim and get it from that forward script that we ran in that other context. But you get the value of that proxy contract, make sure it's the correct one and not the implementation contract. Set that on this script so that it has the proxy address as a constant that it can reference. Now we're setting up some options here. This is a Open Zeppelin library concept that allows us to set the reference contract to the original counter. This way, Open Zeppelin can run some checks to make sure the upgrade is executing properly. By having that reference, it should work properly. We then call upgrade proxy with the proxy address and a reference to the counter v2. Then we create an instance of counter v2 and we pass in the proxy address itself to create that instance. Then we log the count out by calling counter.number. Again, because we got it up to 3 in the previous example, when we run upgrade for the first time, it should run it. It should come out to 3. Okay, on this console output. Then we're going to go ahead and multiply 3 by 3 twice. And basically that's 3 times 3 times 3, which is 27. And it should come out to that when it prints this message to the screen when we run it. So first let's save this. Let's exit out of them. We're back to our console. Now we should run forge clean and forge build, make sure everything's still compiling. Then we are going to execute quick script, forge script. We're going to run that script that we just defined, and it should run against our local Anvil instance. Everything looks like it worked successfully. And if we check our logs, the current count was 3. So even though we upgraded the implementation contract, the count remained the same. So it remained the same from that first deployment script that we wrote, which is great. That's exactly what we wanted. Then we multiplied 3 by 3 twice, and we come out to 27. So this is just a demo of how we were able to upgrade the logic of counter contract, add a new function, retain state after the upgrade. There's lots of additional details to go over here, but for this quick demo, this is a good start and gets you started and comfortable with the idea of proxy contracts and how they work. Um, but if you need more details on this, I highly recommend you check um, Open Zeppelin's GitHub repository and their website. They have lots of great docs on this and how it works. But for now, we'll leave it at that and stop the demo there. But thank you for tuning in.